the song of the heart, it reaches the ear of God. Let's begin this program with the blessing of Lord Almighty. Let's all stand together to invoke God's blessing. Please remain standing for the college song.
Praise be to God beyond all age. Praise be to Bishop Heber College. Let's bring
standing to observe 1 minute silence in respect for the lives of the martyrs of our country, CDS General Bipin Rawat, his wife and other soldiers. Thank you. Please be seated. I would like to know.
Now, I would like to call upon our chairwoman, Ms. J. Janet Seddon, to welcome the gathering.
Good morning, everyone. It gives me a great pleasure to welcome our beloved HOD, Dr. J.G.R. Satyasilan sir, who is a great source of support. I welcome Dr. Rajkumar sir, Head Department of Data Science. Welcome you, sir. It gives me great pleasure to welcome Chief Guest, Mr. Timothy Paul. I extend a very warm welcome to Dr. C. Isaac Sebastian, Head Department of English, Bharatidasan University, and Dr. Lydia Timothy Paul's parents. I also welcome our staff member, Dr. Sophia ma'am, Dr. D. Kirubai ma'am, Mrs. V. Bhuneshwari ma'am, Mr. C. Satish Kumar sir, and all the students to this resourceful event. Thank you.
Thank you, Ms. Janet Seddon.
Now, I request our HOD, Dr. J.G.R. Satyasilan sir, to honor the chief guest with a loving remembrance. Thank you, sir.
Leaders do not force people to follow, they invite people to walk along with them. I would like to call upon our beloved HOD, Dr. J.G.R. Satyasilan sir, to deliver the presidential address.
Esteemed chief guest of today's yet another important event organized by the Department of Computer Science, Master Mr. Timothy Paul. Proud parents who are seated in the front row, Dr. Isaac, the head of the department, English department from Bharatidasan University, and dear madam, the mother of the chief guest of today's event, my fellow professors who are seated with me on the dais, Dr. Sophia madam, Dr. Kirubai, and Dr. Bhuneshwari, and other faculty members, Dr. K. Rajkumar, organizers of this very colorful event. Office bearers, Miss Selin, Chairman and the Treasurer, Surya, and other office bearers. Final years, second years, and first year students. It gives me great pleasure today to be with you in this very cool atmosphere. Of course, outside it is warm, but here we feel comfortable today to come over here through offline mode after a long time. It gives us all an energy. That energy comes through synergy, correct? Because synergy means coming together, right? When we come together, we get energy and synergy also. So this is the success of offline mode, where we see people in person, we share our thoughts, ideas, we get suggestions from others. It's otherwise called peer learning. When I was invited to give a presidential address, I was not really sure about what I'm supposed to talk, how much time I can take, what's the agenda today. But then, the moment I saw the title of today's event, Transcending Boundaries Through Quantum Computing. One thing is proved here, transcending not only the boundaries but also the age. Probably Timothy Paul is of 13 years. It's amazing, unbelievable, transcending the beyond the boundaries, right? Age is not a problem. Age is not a matter, right? When I was having a chance to be seated with him before the event started, I had some conversation to gather some information to talk at least in the presidential address. The moment I allowed him to speak, there was no pause, there was no comma, only exclamatory symbol here and there. He was giving flow of information regarding quantum computing, where he talked about the importance of physics in the computer field. He narrated, he strongly mentioned one point, physics is the base for computer science. Dear students, I think way back 1984, where we, Dr. Sophia Madam and myself joined, we were admitted as students of this college in computer science. That was the time computer science started in Bishop Pepper College. We were the first batch of computer science. But earlier, I had a plan to join either physics or mathematics. Think about my future then. If I had joined physics or mathematics, I would not become head of the department today like this, different scenario. But then, what I want to say now, computer science is not a new subject. It is evolved based on two pillars, I would say, two core science peoples. One is mathematics, the other one is physics. Probably I would have mentioned in some of my sessions, where mathematics purely applications, physics hardware, tangible, intangible, things which we can see, that happens through physics, and things which we cannot see, which we can only feel, that is through mathematics, right? So applications are possible through mathematics. Without mathematics, we cannot survive also, because we have to develop coding, we have to devise a mechanism for steps and all. But physics, it involves a lot of, theories, rules, regulations, everything. So today, I'm also very eager to attend the session, which is now going to be given by our chief guest. Dear students, quantum computing is the talk of the day. Probably many researches are going on that helps computer science to go to the next level. So we are here to listen to this talk to gain more insight and to get more knowledge. With that, we can also go to the research field. Quantum computing is one emerging technology or topic that is very much demanding in the research field also. I'm glad Mr. Timothy Paul is a very blessed person who has gained a lot of knowledge in this field. I think from him we can get more inputs and we can also grow. At this outset, I would like to welcome Professor D. Swamiraj sir, who is the builder of this great institution. We welcome you, sir, on behalf of Department of Computer Science. Without him, it is not possible to have computer science program in Bishop Upper College. We give him opportunity or chance to speak. Now, let me stop my address over to Professor Swamiraj sir to share a few words about computer science, how it started, the purpose, and how we are all here today, the origin of the computer science course in Bishop Upper College. We must know the history of every course. Every course has a history. Over to Professor Swamiraj sir.
Thank you, Dr. Satyaseelan. I'll be very brief. It was the year, I think, 1984, when we started BSc Computer Science. In the whole country, university-affiliated colleges did not have courses like computer science at all. At that point of time, the great late Professor Dr. Manisundaram had the vision and the courage to introduce BSc Computer Science for the first time in a very rural college, namely Nehru Memorial College, Pattanapatti. Second year, 84, the university was started in 1982, separated from Madras University, and Professor Manisundaram became our first Vice Chancellor. And 83, Pattanapatti started. 84, our college and St. Joseph's College started BSc Computer Science. You know, I still remember vividly how the Bishop, late Dr. Paul Raj, inaugurated our computer center. You know how many computers we had? Only 2. In the library, one of the library rooms, not in a separate computer center. And then we started BSc Computer Science. And when that course was completed, there was no college offering any postgraduate course in computer science in the whole of India. So I went to Dr. Jnanam, the then Vice Chancellor, who was leaving for States on that day, and told him our plight. St. Joseph's College, he told me, wanted to start it, but they want the university to give them the computers. I said no. But if you can provide for yourselves, you can start MSc Computer Science, he said. And he called the registrar and told him, give him affiliation for MSc Computer Science, and left for States. That's how we started MSc Computer Science. And then later, we were the first college to start MCA in the year 1994. It was a time when the IT awareness and the IT interest and IT activities began to spread all over the world, especially in the West, and also in Singapore, India, Malaysia, and so on. So when our first batch of MSc Computer MCA students passed out, they were picked up like hotcakes all over the world. And today, I don't know exactly how many, but I guess more than 250 of our MCA students are settled in US alone. And my daughter Sophia's classmate Sati is in Canada, and she is the head of the L&T group there, and she is drawing a salary of nearly 3 lakhs a month, just to give one example. And many of these students who came to MCA according to our college policy were from rural areas. We support specially poor people, whether Christian or otherwise, from rural areas. And these rural boys are now enjoying a very luxurious life in the West and also in the East, like Singapore and also Australia, New Zealand, and so on. I remember one particular boy who came from a small village near Tinnavelly. I was working as a lecturer in MDT Hindu College for 6 years before coming here and assuming charge of the English department in 1966 when our college was revived. One of my students in the MDT Hindu College was one Mr. Jagannathan, and he is now the MD and chairman of Star Health Insurance Madras. And this Jagannathan recommended one of his relatives from a remote village in near Koilpatti. Nagampatti is his village near Koilpatti. And that boy came, and he is now in USA. Once he wrote to my daughter asking for a seat for his sister in a teacher training institute, secondary grade teacher training institute in Periyar Institute. I approached them, they wanted 2 lakhs. Wanted 4 or 3 lakhs or 4 lakhs. And the boy said, I can pay up to 2 lakhs and no more. Just tell you how a rural boy is happily settled there. And this is briefly the story of computer science, reforming the lives and rearranging the lives of poor people from our diocese and neighboring dioceses. Thank you.
Thank you, sir.
Introducing the chief guest. Our chief guest today is Mr. Timothy Paul. Timothy Paul is an author who started his writing career when he was 12. His book Apatine Speaks on Science and Technology was recognized by India Book of Records as being written by the youngest science and tech author in India. He started his YouTube channel called Friendtrin when he was 8. To date, he has made over 60 videos on science and technology. He has great passion for science and technology as he believes in near limitless application for them in improving the lives of people and uncovering the mysteries of the universe. He self-taught and learned computer skills from experimenting and watching YouTube tutorials. He is a multi-talented personality with great oratorical and writing skills. He is 13 years old and studies grade 8 at Mount Zion International School in Pudukkottai. He aspires to be an author and a Nobel Prize-winning scientist. He secured rank 2 in Science and English Language in Silver Zone International Olympiads in 2018 for grade 5. He was one among the top 10 in India in communication skills competition conducted by the TCS ION Intel Gym. From kindergarten to grade 8, he has won a crowing 75 medals and trophies, of which 65 were for first prize. In this lecture, he will talk about upcoming field of quantum computing and his applications in the field of computer science, mathematics, and physics. The lecture will be of great benefit to all those who want to pursue a career in computer science and new computer technologies. He believes that quantum computing is a fascinating field that everyone should explore regardless of their technical acumen. The lecture aims to educate students on quantum computing and its future uses. I would like to invite our chief guest, Timothy Paul, to deliver his speech.
Hello. Good morning. Hello. Can you hear me? Good morning. I would thank you all for being here. I would like to thank Dr. Sophia of Department of Computer Science, who was instrumental in organizing this lecture. I would like to thank Dr. Satya Seelan, who was the convener of the program, and he's the head of the Department of Computer Science, and the other organizer, Dr. Kirubai, and many of the other organizers who worked very hard to make this program a possibility. I understand that your time is very valuable, so we'll try to make the time that we have today as useful as possible for you. The plots of this lecture are threefold. Could you please roll the slide? Could you please roll the slide? Yes, we know. So the parts of the lecture are threefold. What I'll be telling you, what I'll be showing you, next slide please, and ultimately, next slide, what you learn. Ultimately, that is what you will take home today and what will be implanted in your mind about the technology of quantum computing, and ultimately what you will learn and what kind of ideas this will foster in your head and what innovations that will come from your learning of quantum computing. Quantum computing, I believe, will play a big part in the future of computing. It will unlock new possibilities for computing. Though it's still in its fledgling years, that is, it's very young and it's quite an inexperienced field, I believe it has truly great potential for revolutionizing the world of computer science and for revolutionizing the world of physics and mathematics and even aeronautics, right? If it's this powerful today, even just 10 years from the birth of modern quantum computing, quantum computers are so powerful and so capable. I would like you to imagine just what quantum computing can do 2, 5, 10, 20 years from now. Just imagine the amazing possibilities that we'll have with quantum computing. But as Dr. Satya Seelan said here today, we always have to trace back the roots of what computer science is all about. So I would like to explore a history of computing and how we got to this point and how we got to the advancements that we have today in the field of quantum computing. Roll the next slide, please. The history of computing. The history of computing. So I would like to trace exactly how computers came about, how we got to the point of mechanical computers that you know today, that even this slide is being played on a mechanical computer, and how we got to the point of quantum computers and how the first quantum computers were made. So I think it's a very interesting and fascinating history that quantum computers have, and I would just like to explore that history here with you. And so there was a time, right, way back in the 1700s up to the 1940s or 1950s, when computers, they weren't machines like you and I know today. They weren't like laptops or mobile phones. Instead, computers were an occupation. It was a job, like a teacher or like an engineer, right? And human computers, they were indispensable to any operation that involved physics or mathematics. Like, say, you were working in a lab, you would have multiple people who are called computers who would do mathematical operations, often in parallel. So just imagine you are a mathematician or you are a physicist or an engineer working in the 1950s. There would be many computers who would be working under you who would do the tedious operations in parallel. Now, these computers were not seen as a profession to be respected or a profession to be admired, even though they did very hard and grueling and mind-numbing work. They were seen as indispensable, and it was seen like a stair-step position that you would simply have for a little while where you were beginning out, and then they would graduate to being a physicist or a mathematician or something like that. In this image, you can see in 1949, you can see a room of women working for the NACA, or the National Advisory Committee for Aeronautics. Now, something very interesting about NACA is NACA were the precursor to NASA that you and I know today. NASA, that they launched space probes and they launched satellites and they launched Mars rover missions, and I'm sure you know of them. And NACA, they were the precursor to NASA. where today and even back in the day in the 1980s, where NASA uses computers for processing in-flight research data, back in the day, NACA used women like this, computers, human computers, to process in-flight research data. So what they did was they transcribed the raw data from celluloid film and oscillograph paper into standard units. So very fascinating history of human computers. But now, and they were even awarded the 2019 Congressional Gold Medal for, in recognition of their service. They were very unsung heroes, so they were awarded this gold medal for their efforts. Now let's move on to digital computers. You know, the kind of computers that you and I know, the computer that is powering this slide, the computer, little chip that is in the cameras that is being used to take videos of this lecture, and there are many computers, right? But these computers aren't human computers, they aren't mechanical computers, they are digital computers. So let's see the history of digital computers as well, right? And with anything, as it is with anything in technology, the US military was the first to come up with the idea of a digital computer. Now, the very important thing to note, and this will be a recurring topic in this lecture, is how computers operate. They operate in terms of zeros and ones. They are called bits. So let's say you imagine you have 1 bit. That is an empty box. Inside you can have 2 values, either a 0 or a 1. See, imagine it like a switch, a light switch that makes you turn on the AC or turn on the fan or all of these lights that you see in this wonderful gallery here today. When you turn it on, there is an input, there is a signal, and when you turn it off, the light goes off. So it's either 0 or on. Think of it like a switch. But nowadays, where this switch, this so-called switch, is digital, back in the day it was analog. Now, in 1938, the US Navy developed an electromechanical computer that is a computer that uses both electricity and mechanical switch relays on a submarine that goes underwater. Now, this was a weapons-based submarine. It had many weapons that it could fire at enemies, and the computer back then was used to figure out exactly where this missile should be shot so that it hits the enemy. Electromechanical computers, they work in a conjunction of electricity and mechanical. So now think about this. This is the evolution of computers. I'll present to you something of a timeline of evolution of computers. First, there were mechanical computers, like an abacus. An abacus is a kind of rudimentary form of a mechanical computer. Then, in 1938, the US Navy came up with the electromechanical computer. And finally, we come to the days of the Eniac, and we come to Alan Turing's idea of a fully electrical, no mechanical process included computer. Now, Alan Turing, in his 1938 paper, so this is at the same time that electromechanical computers were coming out, he made a 1938 scientific paper. He suggested what is now known as the Turing machine. It's named in his honor. It is basically a blueprint of what modern computers are today. So the modern computers that you see today, wonderful marvels of technology, all of these technologies and the basic framework for what modern computers are today was developed by Alan Turing in his 1938 paper. Even quantum computers, all the supercomputers that you see today that may be in your computer science servers, they are all basically run on the same Turing model or this Turing framework. Now, if a computer can emulate his paper, the Turing machine that was outlined in his paper, if a mechanical computer, a computer that you see in front of you, a real computer, can emulate that computer, it is said to be Turing complete. Now, the first computer to be Turing complete was the ENIAC, or the Eniac, that you can see here. It was a room-sized computer. Now, one of the most fascinating things about computer science evolution that you will learn about today is that computer science evolution, that is the power of computers, is exponential. And this theme of exponentiality is something that you will be seeing often throughout this lecture. Computers do not advance linearly. That doesn't mean that they don't go in units of 1. They multiply in power. As technology gets better, as technology gets more efficient, they do not just simply just go up by 1 unit. They multiply. And just imagine today, this room-sized computer, you have a computer in your pocket, that is your cell phone, you have a computer in your pocket that is millions of times as powerful as this room-sized computer. But for the time, what the Eniac did was simply amazing. The technologies it enabled, the amazing things it allowed us to do at the time were absolutely stunning. And even today, there is no advancement that is as drastic as the Eniac made in its days. Now, here, the whole point of exploring the history of computing here is for me to tell you this. What is the next step? We have electromechanical computers, we had electrical computers, then what will we have next? Like today in 2021, we have digital computers, but our next generation, what computers will they be using? And I say the answer to that is found in quantum computers. All right, let's roll the next slide. Introduction to quantum computing. Now I'm going to give you an introduction to quantum computing and the future technologies that will come up in the field of computing. All right, so we have all studied about atoms, protons, and electrons in physics class, but I don't think we have ever considered their use in computing. When you think about computers, you think about electricity, you think about CPUs, you think about graphics cards, RAM, all that, but you never thought about using protons, electrons, neutrons, all of these, I call them quantum particles. Please remember that, quantum particles. All of these will be referred to as quantum particles. You have never thought of using quantum particles in a computer, but that's exactly what physicists and computer scientists have been doing for the past 1 or 2 decades. All right? Quantum particles, see why would, you may think, why would someone be so mad as to use a neutron or a proton as a computer? But here, let me tell you about some of the weird effects that quantum particles have. See, quantum particles, they do not act like all the things in the real world or the perceived world. If your smartphone started behaving like a quantum particle, it would simply be absurd. Now let me tell you about the behavior of these quantum particles. Quantum particles can be in more than one state. You know, in real life, we hold many assumptions about the way things are. There are concepts such as object permanence, meaning an object, when it disappears, it doesn't go away, right? But with quantum particles, all of these rules are thrown out the window. You can't rely on any of these so-called rules of reality to kind of ground yourself in quantum physics or in quantum computing, right? And one of the best thought experiments to kind of demonstrate this, and you may have heard of it, is known as Schrodinger's cat, right? So there's this thought experiment where where Schrodinger, the physicist, puts a cat in a box, and there's a 50-50 chance. So 50% chance that the cat will survive, or the 50% chance that the cat will die. And what Schrodinger says is, if the rules of quantum mechanics apply to the real world, the cat would both be dead and alive. So, but of course we know that in the real world, quantum physics does not apply. A cat is either dead or it's alive, right? But this specific behavior of quantum particles is exactly what quantum computers use to make them so powerful. Now, let's see exactly how a normal computer functions, or a normal bit, as I said before. Please roll the next slide. A bit. I made this big diagram here to show you how a bit may function. A bit can either be a 0 or a 1. It defaults to either being completely dead or off, or you give an electrical signal to it and it becomes on or 1. Right? So it's like a switch, like the switch for a light. It's either on or it's either off. It can't be a mix of both. But, roll the next slide please. A qubit is not like that. A qubit can be a mix of 0 and 1. Now, this may seem absurd to you, and frankly, it's absurd to a lot of quantum physicists too. A lot of people have been working on this, and even people who won Nobel Prizes. Richard Feynman, who you will see later in the lecture as well, he's a great Nobel Prize winning physicist, and when he accepted his Nobel Prize, he said, if I were able to explain quantum physics in one sentence, I would win another Nobel Prize. So he says that is how hard quantum physics is to explain to someone. So I have taken on this really gargantuan task to try to make you understand exactly how quantum physics works. And really, I don't understand exactly myself either. Now, let's see exactly why this is important, why this power is important. The quantum equivalent of bits that you saw, 0 or 1, is known as qubits. Qubits. Just remember that name. It will be very important later on in the lecture. It's known as qubits. Now, these qubits, as I said before, they can be a ratio of 0 or 1, like 3:10. That is a ratio between 0 and 1. So that is what a qubit is. And when a quantum computer has more qubits, it is exponentially more powerful. A computer with 10 bits is not very powerful, but a quantum computer with 10 qubits is quite extremely powerful, as I will show you in this next slide. Next slide, please. In this slide, a little bit of the bottom part is obscured by the thing, but as you can see here, there's a graph that shows on the bottom axis, you can see the number of bits. 1 bit, 2 bit, 3 bit, and up here there is 10. 10 bits. And this is how powerful a 10 bit is. That is the blue line. It's practically flat. But if you take the orange line, just with 10 qubits, it gives you 1024 units of computing power. Just think about that, with just 10 qubits, right? 10 bits is practically, there's no power. You can barely do calculations. But with just 10 qubits, you can have 1024 units of processing power, or 10 qubits is equivalent to 1024 bits. So just think about that. All right, so the power of a quantum computer is 99%. It is just about the amount of qubits that it has. But as you will see later in the lecture, there is a lot of nuance to the way that quantum bits or qubits function. See, as I told you before, qubits can be more than one thing. A qubit can be an electron, it can be a proton, it can be so many quantum particles, it can be an atom, it can be a quark, and the quality of the qubit matters just as much as the quantity of the qubits, but we will get to that a little bit later here in the evolution of quantum computing. Right now, let me see some milestones for quantum computing. That is, in any technology, right, even the technology of modern computers, or in the on the advancement of smartphones, or in the advancement of even such a very rudimentary thing as a pen, there are a lot of milestones. There are little steps that this technology took to reach the level that it is today. And let's see some of the milestones of quantum computing. First, Shor's algorithm for RSA decryption, right? Peter Shor, who is a quantum physicist, he came up with a quantum algorithm or code. So I'm sure all of you have programmed something in Python or in C++ or in Java. You've coded something, and you coded something like an algorithm, which is basically a set of instructions for the computer. And Peter Shor made a set of instructions that could work in a quantum computer, right? Normal programming, Python is code or instructions for how a classical computer or a normal computer should function, what it should do, print, so forth, input, so forth is this variable, and so on. But Peter Shor made an algorithm, made a set of instructions for quantum computers, right? And what his instruction set could do is, it could crack RSA encryption. Now, one great example of encryption, all of you know, is WhatsApp. WhatsApp does something called the end-to-end encryption, where only you and the person receiving the message can see what the message is about. No one else knows what the message is about, right? A WhatsApp employee can't open the message. So a way to think about this is, if you send a letter in a box, you lock it, and you give your friend the key, and you have a key. You send the box over the post office. The post office people cannot open the lock because they don't have the key. So they just pass the box along, and your friend opens it and sees the letter inside. That is how WhatsApp encryption works. But you see, Peter Shor's algorithm was very interesting because he found a way to open that lock without needing a key. So he found out a way to do RSA decryption on a quantum computer. So this was one great milestone that proved that quantum computers have use in the real world. All right, in 1998, the first demonstration of quantum error correction. See, one of the biggest problems with quantum computing, even today, it was in 1998 and even today, it's one great problem with quantum computing is it's very prone to errors, right? The very nature of quantum computing is that even if one molecule of air interacts with a qubit, the qubit will do something known as wave function collapse. Now, I do not wish to bore you to sleep here, so I will not talk about how wave function collapse works. But all you need to know is it ruins the quantum computing, right? Quantum computing cannot be done properly if an air molecule or there's some electromagnetic interference. So the way around this is through a method called quantum error correction. And in 1998, there was the first demonstration. And even today, one of the biggest fields of advancement in quantum computing is figuring out how to correct these errors that happen so very often because you can't control the environment too well. So third, demonstration of the first superconducting circuit as qubit. Now, as I said before, many things can be used as a qubit. You can use an electron as a qubit, a proton, neutron, atom, quark, many subatomic particles as well can be used as qubit because a qubit is simply a bit of quantum information. And quantum information is relayed in all types of ways. In fact, even the amount of visible light that we see is through a particle called a photon. And a photon, in and of itself, is a quantum particle. So it can be used as a qubit. And in 1999, a man known as Yasunobu Nakamura of the University of Tokyo and Josh Shen Sai of Tokyo University of Science, they demonstrated that a superconducting circuit could be used as a qubit. Now, this was a big discovery because we found out that quantum computers were a viable thing that we could do in reality, and it was a great advancement in the field of quantum computing. Fourth, first commercial quantum computer. In 2011, a company which will pop up a lot during this lecture called DWave, D-W-A-V-E, they made the world's first quantum computer, and they used the aforementioned superconducting circuit, and they made the DWave 1 with 128 qubits that you learn about later. Now, once quantum computing, it became a reality after D-Wave's advancements in 2011, it proved that quantum computers were very real and they weren't just things on paper, and that one day quantum computers could be sitting alongside your desk like a classical computer. Roll the next slide. That's D-Wave. That is their logo. You can see their logo there. Let me show you a few models of D-Wave computers so you can see how the power of quantum computing has evolved. Because this whole lecture has this theme of evolution. At first I told you how computers evolved from a job to a machine. I showed you how they evolved from mechanical switch relays to electromechanical computers a la the US Navy. And then I showed you finally how they became digital computers, and now I'm showing you the advancement of quantum computers. This first model in 2011 is the D-Wave 1. It had 128 qubits. As I said before, just 10 qubits is equivalent to 1024 bits. So just see 128 qubits, do the math in your head, how many bits it's equivalent to. So it's a very large number, it's very good. And this uses the superconducting circuit. But as I said before, many things can be used as a qubit, and therefore the quality of the qubit matters. And in terms of the spectrum of quantum bits, superconducting circuit qubits are the lowest. They are the least powerful qubit. Qubits in and of themselves are very powerful, but a superconducting qubit is the least powerful. And next model, please. In 2013, they made the D-Wave 2 chip with 512 qubits. And you may think it's just a 4 times increase in power. But if you remember what I said before about exponentiality, you will learn that it is over 2 to the power of 384 times more powerful than the original D-Wave 1. Right? And that is a number with 116 digits. So if you were to write that number out on a piece of paper, this piece of paper will be as big as me. You'll need a wall-sized piece of paper to write this big number down. And in fact, this number is more than the amount of grains of sand on Earth. So that's an interesting fact for you. And if you want to keep up to date, next slide. If you want to keep up to date with DWave's advancements in quantum computing, and you want to know what kind of troubles they've been facing and what scientific advancements they've made, you can check out this website, dwavesys.com, dwavesys.com. And it's a very good website where they share exactly what kind of technologies that they have to go through in order to make DWave, let's say, 3 a reality. One of the other big, next slide please. One of the other big kind of computing giants, quantum computing giants, is IBM. Now you may have heard about IBM back in the old days when they made a lot of kind of consumer grade computers, where they made computers that you and I would use. But nowadays they're more enterprise facing. They make computers for companies, and therefore they saw great promise in quantum computing. And let's see what are the kind of computing systems that they've come up with. Roll the next slide, please. This is the IBM QSystem 1. I'm not sure if you can see it properly, but it's very beautiful. It's in a glass case, and it looks like something from a sci-fi movie or something from space, and it has 10 qubits. Now, this may be quite disappointing to you. It has only 10 qubits, whereas, just as we discussed before, the DWave 1 has so many qubits. It has 128 qubits, and the DWave 2 has 512 qubits. And you're telling me that IBM, such a big company, comes out with some measly 10 qubits. But again, as I told you about the quality of qubits, this is a completely circuit-based quantum computer. Now, the DWave 1 is superconducting based. And I said, in the spectrum of quality of qubits, superconducting is the lowest. And circuit-based is on the higher end of quality qubits. So 10 qubits is not that far away in terms of computing power. 10 circuit-based qubits is not that much worse than 128 superconducting qubits. But that's not bad, because right now, over the course of 5 or so years, they will come out with 27, 32, 62, and 127 circuit-based qubit chips. So this was just a prototype, but even that wasn't that not powerful. It was very powerful. So the number of qubits doesn't always matter. You have to also think about the quality of the qubits. That's something to keep in mind as you kind of get a career as a computer scientist and you have to come across quantum computers. You should remember that the quality of qubits matters a lot as well. And here you can see, as I said before, you can see the IBM QSystem 1. That's its name. Very long name, so I don't bother saying it every time. IBM QSystem 1. And please roll the next slide. And here you can see a timeline of IBM quantum computing chips. So they announced a roadmap, and they say that by 2023, they'll have a quantum computer with 1,121 qubits. So many advancements have been made. Just from 2019 alone, they have been doubling, tripling, even quadrupling their qubit count yearly. So I don't think 1,121 qubits is too far away. And then in the future, they're aiming for, in 1 decade from now, they're hoping to have a quantum computer with 1 million qubits. And one of the great things about having 1,000 qubits is, when you have a quantum computer with 1,000 qubits, it can execute Shor's algorithm. This is why I mentioned it earlier in the lecture. So if someone were to get if someone malicious were to get a hold of 1,121 qubit quantum computer, they could just hack or decrypt RSA encryption using Shor's algorithm. So that is something to keep in mind. But as you will see later, that may not be a problem, because the people, that's like WhatsApp, they will get their own quantum computers, so they can quantum encrypt their messages, and so that it makes it difficult to quantum decrypt. And that I'll get into later. Now let's look at the next company. This one must be very familiar to you, Google. Google has also done a lot of research in regards to quantum computing, and in fact, they are the first company to claim that they have reached quantum supremacy. Quantum supremacy is basically the state where a quantum computer does something that a classical computer cannot. That is, a quantum computer accomplishes something that with a normal computer, even a supercomputer, you just cannot hope to do. And Google claimed that with their 53 qubit, next slide please, with their 53 qubit Google Sycamore chip, they say that they did an operation in 200 seconds that it would take a normal supercomputer 10,000 years to do. Now in the next chapter we will see exactly how valid their claims are, and we will see the evolution of the concept of quantum supremacy, and we will also see about the attempts at quantum supremacy in the next slide. Now, quantum supremacy is a word that was coined by a man by the name of John Preskill, who you can see in this slide here. He's a MIT researcher. He works at he first worked at MIT, and now he works at Caltech, and he coined the word quantum supremacy to mean the point in time where quantum computers surpass and ascend above and exceed classical supercomputers in every imaginable way, right? And the explanation, a lot of quantum physicists, they say that quantum supremacy is physically not possible. They say that due to the way that physics is, they say that due to the very fundamental framework of physics, quantum supremacy is not possible, and they say that the very rules of quantum mechanics forbids it. And that is a claim that is yet to be validated, and we'll have to see in the future with future technologies exactly how this quantum supremacy ordeal pans out. Now, Peter Shor's algorithm is actually one way to check if a computer has reached quantum supremacy. As I mentioned before, a 1000 qubit computer could execute Peter Shor's algorithm, and that is because Peter Shor's algorithm is a test for quantum supremacy. So a computer with 1121 qubits, like the IBM QSystem one, could be a computer that can reach quantum supremacy. All right, to achieve quantum supremacy, right, they would need to take advantage of resources that only quantum computers have. Right? Just think back to what I said. What are some things that only quantum computers can do that classical computers cannot? Now, what a computer that can achieve quantum supremacy will have to do is that computer will have to take advantage of things such as superposition, quantum superposition, and quantum entanglement in order to achieve quantum supremacy. So let's see how researchers are going to do that, right? And now this has been the subject of a feud between Google and IBM, right? Google claims that they have reached quantum supremacy, and IBM, who also have skin in the quantum computing game, they say that no, Google has not reached quantum supremacy. They say that their papers, that the research papers are fraudulent. Not fraudulent, but they say they're dubious, right? That's the word they use. They say their papers, their claims are dubious, and they say that quantum computing can only reach quantum supremacy in a decade, right? That's the timeline that they've given for quantum supremacy. But let's see exactly what Google has did, right? I'll read from here, which is an excerpt of what Google has said they've done, right? Google used a 53 qubit processor to generate a sequence of millions of numbers. Though these numbers appear randomly generated, they conform to an algorithm generated by Google. A classical supercomputer checked some of these values and they were correct. Google's quantum computer named Sycamore claimed supremacy because it reportedly did the task in 200 seconds, which would have apparently taken a supercomputer 10,000 years to complete. Now, that's a very bold claim, and it's a very kind of surprising claim coming from Google, but they say that they did it in 3 minutes, right? That's 200 seconds, 3 minutes and change. And they say that if a supercomputer, even the world's fastest supercomputer, ironically, which is IBM supercomputers, if they were to attempt that, they say that it would take that computer, it could take it 10,000 years. Just imagine that. We'll be 500 generations from now. They say it will take that long to complete. Now, here I'm reading an excerpt from experts. Very tricky word to say, excerpt from experts. They say that this does not imply that a quantum computer can solve every challenging problem thrown at it. The number generating task was the equivalent of having a Ferrari and a truck compete in a race, and on the car's predictable victory, declare that a Ferrari could do everything that a truck did. While IBM and a few other private establishments also have quantum computer prototypes, a common element is that they have their own unique propensity to errors and are not as amenable as at executing real-world problem as supercomputers. So they say that they're saying that quantum computers, okay, they may be more powerful in this one task, but they are not as reliable and they are not as consistently powerful as classical computers, as classical supercomputers. And that's a very fair claim. And that is exactly what the kind of current advancements in quantum computing are trying to fix. They are going for better error correction and better speed. All right, so let's look at the next slide, the future of quantum computing. And I think this is really the crux of the message here. What is the future of quantum computing? Right, today it can do this and that. And as I posited earlier in the lecture, if it can do all these things today, what will it be able to do with its exponentiality 5, 10, 15, 20 years from now? I think quantum computing has a truly, and I mean this not lightly at all, truly amazing golden future, right? And I don't see quantum computers completely replacing classical computers in our lifetimes, or in our children's, or in our grandchildren's, great-grandchildren's lifetimes, right? I believe that the classical reliability is completely unbeatable, but I think that one day you will find your computer with a classical chip and a quantum chip alongside it. I think the power of a quantum computer is unmatchable, but also the reliability of a classical computer is unmatchable. So in the future, I see both of these technologies being used in conjunction to enable great technologies reliably. That's the key word here, reliably. Right? Quantum computing may revolutionize every single area that computing is relevant in. And in the modern world, quantum computing, and by extension, modern computing, is in everything. There's a computer in the camera. There's a computer in that camera. There's a computer in our pockets. There's a computer in the smart board. There's a computer in this mic that it can be seen as some sort of a computer. There's a computer in everything. And because I say that quantum computing revolutionizes computing, and computing revolutionizes everything, by extension, quantum computing will revolutionize everything. Right? It will change everything. It will for the better. Right? I truly believe that in tomorrow's world, quantum computing will be a very common topic, and that's why I'm here telling you all this information about quantum computing, because in the future, if any of you decide to go for careers as computer scientists, I think 10, 20 years from now, definitely you will have to encounter quantum computing in some capacity, because quantum computing will find its way in every little corner of computing. And when you have this head start, now that you know all about this, I think you'll have a great head start in the future where quantum computing is in all facets of computing. And one of the other big things about it is that quantum computing and physics are now intertwined. Right? The physics was quite disconnected from computing in general around the 1960s, because at first, computing itself was made for war. It was made in 1938, as I said before, for the Navy torpedo-firing missiles. And then in 1940, Alan Turing made a computer to crack the Enigma code, and it's been used for war. And then it was used for physics in NACA. Right? After they stopped using human computers, they used the Eniac. Right? In NACA, they started using computers for physics. Then they started using them for math, and then we had this disconnect. Physics kind of disconnected from computing. But now it's been reunited with computing in the form of quantum computing. And I think only great things can come from this match. So I truly believe that, especially as Dr. Satyasilan said, the physics background is very important as well in terms of computing. And there's also great potential for quantum computing in aeronautics as well. And quantum computing, it will really cover every single facet of our future existence. So just please keep that in mind. And with that, I would like to just emphasize the importance of the topics that you learned here today. Quantum computing will be in every corner of the future. And with that, I would like to conclude this lecture. And I would like to ask if any of you have any questions, because this has been a very long and arduous lecture, and there have been many points. And if any of you have any questions about anything that I've discussed in the lecture, I would like you to please stand up and ask me the questions so I can answer them and clear them for you. Yeah.
Young Mr. Timothy Paul, thank you very much for your wonderful talk today on quantum computing. I have a few questions
Yes.
as an ignorant man. Number one, when was the first computer invented and used, and in which country?
I think in my opinion, I would say the first computer. I think it really largely depends on your definition, but I think I would consider the computer that the U.S. Navy made, the electromechanical computer in 1938 by the USA.
I see.
So I would consider that. But if you were to go for largely only electrical computers, I would say it's the Eniac. But in terms of country, definitely the US was at the cutting edge of computer science.
I see. How do you compare the computer wherewithal in China with with that in US?
I think what China is doing is they have really big numbers. One of the in the models of quantum computing, I didn't cover this one quantum computer, and that's for good reason. What they have is they have large amount of qubits. They have 5,000, 10,000 qubits. But the thing is, as I said before, quality of qubits matters. But China, but their innovations in science, the thing is, when one entity innovates, everyone benefits from it. So I think what work that China is doing is very great, and they are at the cutting edge of quantum computing and also computing in general with their big server farms, and because they have economic incentive as well. But I think in terms of how history will remember them, they'll be quite insignificant, but the work they're doing is great and admirable.
Third question and final question.
Yes, definitely.
What is quantum computing to do with the so-called supercomputers?
Yes, quantum computers, they are also supercomputers. If supercomputer is any big powerful computer, quantum computers are also supercomputers. What they have to do with supercomputers is they are competing, right? A supercomputer is trying to outpace quantum computers are basically trying to outpace supercomputers. So it's like a race. The quantum computers are trying to be faster than supercomputers. So it's like they are like rivals. So that's what I'm talking about in the lecture. Thank you so much for the questions.
Dear students, I'm very happy that Mr. Timothy Paul has given a detailed lecture on quantum computing, which will be future, right? Which will be the talk of the day in future. Definitely a lot of researches are going on. More questions are expected from your side. If you raise questions, Timothy Paul is ready to answer any sort of question at any level. Anybody?
Yes.
You can represent qubits as a ratio of 3. So can you elaborate on that?
Yes. So basically, in one way to visualize it is as numbers. So in bits, we have 0 and 1, on or off. And when you think of it in terms of numbers, a qubit can be a ratio of on or off. So they can be a ratio. That is, they can be or a fraction, because that's how maths works. You can make a ratio into a fraction. So let's say that it's like, rather than a switch, it's like a slider. You know, they have sliders on some ACs, like a blinder. They have sliders. So it's like a slider. So it's three fourths as well, you can say.
Can both represent a 0 and
Or
as
a
well
1. It can be a 0 or a 1, like a bit. But it can also be 3/4 of 1. So you can be, rather than from being here or here, it can stand somewhere in the middle. And that's why it's so important.
It's like a fuzzy logic. the things that you represent in a fuzzy logic.
Yes, yes.
So it's not definitely a 0 or not definitely a 1.
not definitely a 0, no, no, no.
Definitely
But the
a one.
problem is, that's why errors happen a lot, because when something else collides with the qubit, what happens is, it's like the slider, the spring in the slider breaks. So it goes, it will default, it'll kind of round to 0 or round to 1. And that's the problem, that it'll ruin the qubit. It will make the qubit like a bit which will make it useless. So what they have to aim to do is, they have to keep all of these pollutants, the air particles, they have to keep all the electromagnetic radiation away, because if that hits the qubit will just forget about being a qubit and will decide, I'm either going to be 0 or I'm either going to be 1. So that ruins the qubit.
You have to be very careful about the preciseness, the accuracy.
Yes, yes, yes.
Thank you.
Thank you so much for the question.
What is your motivation to study quantum computing, and when did you and how you start this?
So I encountered quantum computing when thinking about new computing technologies. So computers, at least for my lifetime, they've been very stagnant. So they simply get faster, the nanometer diodes get smaller, and I found that quite boring. So I thought, what's the next stage in computing? Right? What is the next big generational leap? Right now you have Intel and AMD, they make chips and they have smaller and smaller and smaller transistors, they have bigger and bigger chips, and I wanted something different, an entirely new world, if you will. And I thought quantum computing is this next big field, and as I started looking into it, I have great interest in physics as well. I am very interested in quantum mechanics. Right? In the book that I've written, and in the book that I'm writing now as well, it's a new book I'm writing, quantum mechanics plays a big role, because it is the very fabric that underlies our universe and underlies our existence. So when I learned about quantum computing, I found it to be great. There's this entirely new world of physics out there that can be applied in computer science, and we can do things that are completely different. So it's not just like the boring old computers that we are used to, it's not more powerful laptops, it's an entirely new world, and that was extremely fascinating to me. And once I learned how useful it is in the real world, I really felt like, as this opportunity came up, and Dr. Sophia suggested this to me, suggested that I do a lecture here, I was very interested, and I wanted to do a topic that would really benefit the audience. So I came up with this, and I think quantum computing has so many uses in the real world that I definitely had to share it with you. So that's my motivation for learning quantum computing, and for especially choosing that as a topic to speak here instead of the umpty number of topics that are out there. Thank you so much for the question.
Students, more questions. Will be given more answers also.
Hello. Does it work? Where you get inspirations? How you increase your interest in quantum computing and computers?
Yeah, it's quite a similar question to what I was asked before, but yes, it's a good question. I think what you mean is how I get the information on quantum computing, right? No, I know, I heard the word correctly, but you mean like, I got the inspiration, if you want specifics, I got inspiration when reading Richard Feynman's biography. It's a wonderful book. It's quite a humorous book too. It's about his life. He has anecdotes. It's called Surely You're Joking, Mr. Feynman. It's a wonderful book. And when I was reading there, he was talking about his tenure at MIT, working as a student as he was studying as a student, and he was talking about his interest in quantum mechanics. And that was the, if you want really specific inspiration, that is exactly what sent me down this kind of rabbit hole of learning about quantum computing. So if you want specifics, it was Richard Feynman's biography, the first one, Surely You're Joking, Mr. Feynman, on chapter 8 or something, I think that is. So that's the specific inspiration for quantum computing. But more generally, I just really love the idea, I love the concept of quantum computing. So if you want to be general and specific, those are the two answers. Great question, thank you very much.
Hello. It's for the benefit of the students. Timo,
Yes, hello?
here.
Where are you? Yes.
Can you name a few books? Can you prescribe a few books or links
Yeah.
that will be helpful for the students to learn about quantum computing? Since quantum computing is going to be the future,
Yeah.
can
yeah,
you prescribe a few books for the students to learn about quantum computing?
Definitely,
They
definitely.
can make a note of all the books.
Definitely, definitely. It's a great question because I'm all about my ideas are that you should always go back to the root. Right? Whenever you want to learn about anything, you should go back to the people who invented it and came up with it. And in terms of that, I have a few book recommendations for you. First would be, as I said before, Richard Feynman's autobiography, where it's also a very entertaining read. It's a very wonderful kind of insight into his mind. He's a Nobel Prize winning physicist, quantum physicist. So it's great, you should read that. He has 3 biographies, I think. One of it is Surely You're Joking, Mr. Feynman, and the second is What Do You Care What They Think. And those 2 books are amazing, I think you should check them out. And the other recommendation I have is Stephen Hawking's Reith Lectures on Black Holes. So on BBC, similar to this lecture, he gave a lecture on black holes, and it was a transcript of that. It's a very small book and you will learn a lot from it. Not only is it about black holes basically they break quantum physics. So if you want to know about quantum physics, I think it's good if you know what its limits are. So you can go read Stephen Hawking's Reith Lectures, and you can also read Einstein's autobiography, The Way I See It. So it's a wonderful autobiography. I am all for autobiographies instead of very specific books written only about science, because you get a window into the way they think. If you see how Einstein thinks about things, how such a brilliant mind, how he processes the information, you can process the information about quantum mechanics and physics too. So I would recommend, in terms of what I've read, I would recommend The World as I See It by Albert Einstein, the BBC Reith Lectures by Stephen Hawking, and last but not least, Surely You're Joking, Mr. Feynman by Richard Feynman. So they're wonderful books. So those you can learn if you want to learn about quantum computing. And so they basically give you like a quantum physics 101. And from there you can use your existing knowledge of, your very extensive existing knowledge of computer science, and that together you can learn a lot about quantum computing. Thank you so much for the question. Wonderful question.
I would have expected more of you to have asked questions, but not bad. When I was in Madras Christian College doing my MA English, there were meetings of other subjects which I invariably attended. And at every meeting there, the practice was, after the lecture, there will be an equal length of time given for questioning the lecturer and getting clarifications on the points raised in the lecture. this is a very important part of any meeting. Any meeting to be useful to the students should not just be a lecture and thank you, but lecture followed by question. I am glad so many have come forward to question the lecturer. And the lecturer, I am told, is doing his 8th standard. It's amazing how an 8th standard boy, I would call you a boy, forgive me, is addressing, should have been addressing MCA and MSc computer science students today. I asked the head of the HOD why they didn't come. I don't know why, but they should also come. But I'm glad you are able to address these undergraduates here in our college. And I do hope and pray that one day you will be more than a Sundar Pichai of Google or Mr. Parag of what is it? Twitter. God bless you, boy. Thank you.
Thank you so much. Thank you so much, sir. Thank you so much. And in the end, I would just like to thank you, the audience, for being patiently with me here today for almost an hour now, it seems. So I would thank you so much for being here, for your patience, and for your attention. Thank you so much. I hope you take this home and you think about it and you learn about it. Thank you so much.
Thank you, sir. Appreciation can change a day, even change a life. I would like to call upon our treasurer, Mr. P. Surya, to deliver the vote of thanks.
Hello. Good morning, everyone. First and foremost, I would like to thank our Lord Almighty who was with us from the beginning till this moment of our event. And I next extend my heartfelt thanks to our chief guest, Timothy Paul, who spared time from his busiest schedule to grace the occasion. Today, we had an opportunity to hear your thoughts, and this will surely going to encourage us in our future event. Thank you, sir. Next, extend my gratitude to our ever-dynamic head of the department, Dr. J.J. Satyasilan, sir, who has been a pillar of support to the student body in all we do. Thank you, sir. Moving forward, I would like to thank our SF department HOD, Dr. Rajkumar, sir, who has spent this precious time with us to make our lives better. I also thank all faculty members of excellent department of CS for their tireless help and support. It will be an utter failure if I fail to thank and acknowledge the eccentric support provided by our students, friends, without whom this day would have been like any other normal day. It's now time to wind up my vote of thanks, and I feel with sense of gratitude in my heart as I finish my speech here. Thank you one and all. Have a great day.
Thank you, Surya.
I would request everyone to kindly stand up for the national anthem.
मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you all. As the dignitaries are leaving the dais, please remain standing.